Yeah. 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 Good evening, one. So before I start, can anyone please confirm whether my voice is clear, whether the screen is visible or not? Yes.
Yes, sir. We can see your screen.
So in the yesterday session, just I was briefing you about Apache Spark, why PySpark, need for PySpark, and comparison between Python and Scala and PySpark features, real life usage of PySpark and PySpark job market, right? Yes. So yeah, starting with this, right? Yes. Today. Evolution of Spark. Evolution of Apache Spark, right? Yes. Spark. Spark was developed by the personality who developed Spark, Matai Zaharia, in AMP lab. In AMP lab, Berkeley. So it was developed by Matai Zaharia in AMP lab, Berkeley, in the year 2009. It was introduced in the year 2009, but Spark was open sourced. Spark was open sourced in the year 2010. Spark was open sourced in the year 2010, right? Spark was donated. Spark was donated to Apache Software Foundation. Apache Software Foundation, right? Yes. In the year 2013. So Spark was donated to Apache Software Foundation in the year 2013, right? Yes. Yeah. It was developed by Matai Zaharia in the year 2009, was open sourced in the year 2010. Spark was donated to Apache Software Foundation in the year 2013, right? Yes. Ah, Spark, defining Spark. So why Spark? As I define Spark in 5 lines. Yes, Spark is a yes. It is a open source distributed cluster computing framework in parallel processor style. In parallel processor style with with in-memory computing feature. With in-memory computing feature. Yes, used for large scale data processing. Used for large scale data processing, right? Yes. So Spark, so open source distributed computing cluster computing framework in parallel process style with in-memory computing feature used for large scale data processing, right? Yes.
You want to quickly elaborate this in-memory computing feature, Vijay?
That's what I'm going to say, right? In-memory computing.
Thank you.
What do you mean by in the main feature? All this you can see in Hadoop, right? Open source, distributed, parallel process, large scale, except this everything you can see in Hadoop, right? In Hadoop MapReduce. But only thing is in-memory computation is an extra feature we see in Spark, because of which we got very high speed, right? Yes. Here, in-memory computation, data gets loaded into RAM, not into disk. Data gets loaded into RAM and data gets processed. Data gets processed within RAM. Data gets loaded into RAM and data gets processed within RAM. Here, data is divided into partitions. Data is divided into partitions, and the partitions distributed S. Data is divided into partitions, and the partitions are distributed across multiple RAMs of multiple worker nodes. And are processed parallelly. Right? Yes, that's why we see very high speed in case of Spark. So here data gets loaded into RAM and data gets processed within the RAM. It's a general engine for big data analysis. Spark is a general engine, right? Yes. It's a general engine for big data analysis, big data processing and computation. And why, okay, why PySpark? It is a Python API to use Spark. It's mainly used for creating data pipelines, for ingesting data into database, running ML algorithms, working with the data streams. Yes. Need for PySpark, Python and Spark combined together, right? So it has got many flexible options for the world of big data. Yes, Spark can be coded with, Spark can be coded with Scala language, Python language, Java language. Yes, multiple, it supports multi-language. Spark as multi-language support, right? It can be coded with any of this language, mostly used one, Python and Scala. Python and Scala, right? Yes. Yes. Python, it's a difference between Python and Scala, both it's dynamic types, it's statically typed. Python is slower as compared with Scala. Scala is faster. Python has a huge community as compared with Scala, and Python has got powerful libraries for this, especially for this ML data science, that is graph algorithms, right, and data streams. Okay. PySpark features. PySpark features in-memory computation, lazy evolution. Okay, in-memory computation means just now data gets stored. Data gets stored processed within data gets stored in memory and processed within the RAM. Lazy evolution. On demand what do you mean by lazy evolution? On demand executing the flow. On demand executing the data flow. Until then it won't execute automatically. On demand executing the data flow. Spark has the capability. What is the powerful fault tolerant means? Spark has the capability. Back the lost partitions. See, when I here data is divided into partitions and the partitions are distributed across multiple RAMs of multiple worker nodes. Suddenly, if any worker node gets down, right? If any worker node gets down, there is a data fail, right? So Spark has the capability of getting back the lost partition also, right? But yes, immutability. Spark data objects, Spark data objects. Spark data objects, what we are going to discuss, right? RTDs and data frames. are immutable, right? The original data object will remain same. It won't be modified or changed. Persistence, right? We can reuse the already executed transform already. We can reuse the already executed. What is it? We can reuse the already executed transformation output. Already executed transformation output, right? And partitions. Spark data object divided into partitions and are distributed and are processed parallelly right? Yes. Real life usage of PySpark, right? Yes. Used in the commercial sector, right? In banking sector, in other financial fields, they are using PySpark for real-time processing. In healthcare, in identifying or predicting the health status, and entertainment industry like Netflix using PySpark, right? For the online streamings. E-commerce for advertising and recommendations like Flipkart, Amazon, and for tourism industry in guiding this tourists. Yes, as I was saying, right? Just showing you how he has taken a table of 100 TB consisting of 1024 columns. Task sorting based on 16 columns. What is the time taken, right? By different databases. Oracle has taken 3.5 days. MySQL has taken 6 days. Teradata has taken 4.5 hours. Netija. Hadoop has taken 3.4 minutes. Hadoop is 100 times faster than Hadoop. Already Hadoop speed is very less, right? As Hadoop has got very high speed, but still Spark speed is 100 times faster than Hadoop. Just imagine the speed of Spark because of in-memory computations. And if you observe this, yes, execution generations, if you observe this execution generations, yes, initially, first like map reduce, we had Hadoop map reduce. Map reduce is a parallel execution model. Yeah, what Tej, Spark. They're comparing Spark with different. You can say why Spark has got more advantages as compared with other processing technologies, right? So comparing, right? If we okay, MapReduce, okay, it has got some okay, I'll discuss about MapReduce and Spark later. But coming to this Tej and Spark, comparing MapReduce and Spark is nothing but comparing Hadoop and Spark. Okay, I'll come back to it. But before that, Tej and Spark. These two. Both follows DAG model, DAG. DAG means directed acyclic graph. Both follows directed acyclic graph model. I'll discuss about this DAG, but it both follows DAG model. But here, Tej doesn't follow in-memory computation. Tej doesn't follow in-memory computation. It doesn't follow in-memory computation. So Spark has got high speed. Spark has got high speed as compared, right? As compared to Tej. Yes. Sage doesn't follow in-memory computation. So Spark has got high speed as compared to Sage. So yeah. Now comparing, what are the other in-memory computation technologies? Other in-memory computation, other in-memory systems, other in-memory computation systems in the market, right? SAP HANA. SAP HANA is also in-memory computing systems. We talk about HANA and Spark. HANA and Spark, right? So both follows in-memory computation. Both follows in-memory computation. But HANA is not distributed. But HANA is not distributed. The Spark is distributed RAM. Spark has distributed RAM. So for example, if after, for example, you got some memory, right? Storage for HANA. After some days, it gets filled. It cannot support further, right? So if you want to load some new data, right? The old data has to get removed, right? But Spark, you can keep on. It has got distributed RAM. Depending upon the incoming data, you can keep on adding, right? Increasing. Yes. So for huge storage, right? Yes. Hadoop, HDFS, and for fast processing, right? Yes. Spark. Combinedly, yes. Combinedly, both can store and process. Combinedly, both can store and process huge data, right? Yes. Understand here? So for huge storage Hadoop, for fast processing Spark, combinedly both can store and process huge data. Yes. And one thing what you need to understand, right? Hadoop or Spark, they are mainly designed for they're mainly designed for batch applications. They're mainly designed for batch applications. Millions and trillions of records, right? Not for a single transaction or two or three, right? So for huge transaction, for batch applications, and for iterative algorithms. Right? Most of these data science algorithms, ML algorithms are iterative in nature. So we keep on applying the same algorithm on the input data until the error becomes zero, right? For interactive queries, they're mainly designed for interactive queries, some kind of querying, right? Yes. For interactive queries and for streaming. So Spark mainly designed for batch applications, interactive algorithms, iterative, that is interactive queries, and for streaming. Okay. Spark, this PySpark supports, right? PySpark supports advanced analytics. It supports advanced analytics, right? It's like machine learning. It supports advanced analytics for this machine learning, graph algorithms. For streaming and interactive queries. So now, difference between MapReduce and Spark. MapReduce and Spark, right? Means Hadoop MapReduce, right? Total MapReduce execution is going to happen, right? Previously, map is a well-designed model, right? MapReduce is a well-designed model. It's used for parallel executions. Was mostly used previously, but once Spark has come, right, the usage of this MapReduce has decreased a lot. You see the difference, main difference, what are the MapReduce drawbacks? MapReduce drawbacks. First thing is transformations cannot be reused. Transformations cannot be reused. For example, transformations cannot be reused. For example, you're performing some kind of aggregations today, right? For example, 1 second. A small task, if I take, if you are performing some aggregations, you got some data. Column 1, column 2, column 3, in this way, some column 30 columns are there. So you want to perform some aggregation. Groupings, you want to perform grouping and aggregation. For grouping and aggregation, grouping on one column, aggregation on another column, 2 columns required. So first what you will do, you will extract these 2 columns, column 1 and some column 4. Only these 2 columns only you will extract it. You are going to extract this column 1 and column 4. After these 2 columns are extracted, this step. After extracting this steplet, you will get, for example, column 1, comma, column 4. Yes. After that, you perform aggregate. What is it? It's perform that operations, right? Grouping on which column, aggregation on column. Today you perform like some aggregation. Assume that you perform some aggregation. So city-wise total revenue. So some city-wise total revenue means yes, city-wise total price. Which are the 2 columns here? You have extracted city and price. 2 columns. City-wise total price you want. Total price means some aggregation. So what you did, this entire thing you did some, here you have extracted city and price. So how this process is there of extracting, right? City and price. Tomorrow I want to perform on the same city and price. Say from the same city and price, I want to perform average aggregation. But what happens? Directly I cannot take this output and perform average. We need to reinitiate from the starting. Every time we need to reinitiate from the, we need to re-execute from the starting. Already executed, already you have got this output, right? City and price, the same thing you use and perform average. No, you need to reinitiate, re-execute. You cannot reuse the already executed transformation. Tomorrow, day after tomorrow, I want city wise, I want what is the max revenue, max price, max or min. If you want to perform this kind of aggregations, still again, you cannot reuse. Again, every time you need to reinitiate or re-execute from the beginning, right? We have got mapper task, reducer task. Mapper task is going to perform this, right? In MapReduce, mapper task is going to extract this columns. Reducer task is going to perform this aggregation, right? So mapper task output you cannot reuse again for the tomorrow. If you want to perform any operation, again you need to re-execute the mapper task. Again, you need to get this output. Again, on this, we need to perform this. Without initiating mapper, directly reducer, you cannot execute. Every time your reducer logic is, reducer transformation is changing. So directly, always my mapper logic is same. Directly, why can't I take the mapper logic and directly go with the different reducer transformation? No. Every time, even though if mapper logic is same, every time you need to reinitiate. Without mapper, you cannot have reducer task. Map reduce means mapper and reducer two will be there. Without mapper, reducer can't be executed directly. Every time, even though the same task or same transformation, again re-execute the mapper and get its output and store it. And because mapper output is taken by reducer, mapper output should be taken by reducer. Without initiating mapper, directly reducer cannot get the output. So every time transformations cannot be reused. And here other drawbacks, right? If you see MapReduce and Hadoop for this ML algorithms or for this data science, right? So little weaker as come. Okay. So bad for iterative algorithms. Bad for iterative algorithms. If you heard, there is a component called Mahout previously for this machine learning kinds of this, right? For ML kinds of algorithms, right? So it's bad for iterative algorithms. Means the data science algorithms are iterative in nature. We keep on executing that algorithm. We'll be applying on the same input data until the error becoming, and not a flexible parallel process. Not a flexible parallel process. Which one? MapReduce is not a flexible parallel process, right? It's parallel process. Why it's not a flexible parallel process? Yes, mapper reducer. Mapper output is taken as the input by the reducer. Mapper and reducer, can they execute parallelly? Mapper and reducer, can they execute parallelly? MapReduce is designed for parallel processing. You got a mapper. This mapper output is taken as the input by the reducer. Reducer output finally it is stored, right? It's taken. But without, okay, can you execute this mapper and reducer parallelly? MapReduce is designed for parallel processing, but this mapper and reducer, can it be executed parallelly? No. Until mapper execution completed, reducer cannot execute, because once mapper output is completed, its output has to be given as input to the reducer. Once it is taken, then input, the reducer then gives that output, but both can't execute in parallel. But here, not a flexible parallel process, right? Yes, that is. And slow processing, right? Which one? MR. Slow processing means Spark is 100 times faster. Spark is 100 times faster than MR or Hadoop. So these are the drawbacks of this MapReduce, that is Hadoop, as compared with Spark. Spark has got its own execution model. Hadoop MR has got its own execution model. Both execution models are different, not same. And most of them students keep on asking, Spark is not a language. Spark is an execution model. MapReduce is also an execution model. Two different execution models, right? Yes. Now, there is one more. Previously, yesterday I was saying you, right? There was one more component in Hadoop which was mostly used in the previously, right? Very much used, very flexible with very less coding, right? Pig. Spark and Pig, right? Apache Pig. So the commonality, what you see in Spark and Pig, both are data flow. Both are data flow languages. Both are data flow languages. Means data, the entire flow will execute when we perform some kind of. But in Pig, entire data flow is converted. Entire data flow is converted into one MR job, one MapReduce job, right? But in PIG, entire data flow is converted into one MapReduce job. But again, MR is bad. So internally, PIG processing happening within the MapReduce, right? But so when PIG following MapReduce, entire data flow is converted into one MapReduce job. So in PIG, the entire data flow, right? X. So again, MR is bad. Okay. So from this differences, what we have seen with different technologies, right? So now try to say like PySpark features and advantages. Advantages, what? One thing, what is the advantage that we have got as compared with Tej?
Vijay, MR means
MR means MapReduce. MapReduce. So, but again, okay, into one MapReduce job, yes. One MapReduce job. But again, MapReduce, right, is bad. Means in Hadoop, MapReduce execution is going to happen, right? Mapper and reducer will be there. So, already I said MapReduce drawbacks. So, but what happened in the case of PIC? Entire data flow is converted into one MapReduce job. Again, MapReduce is bad. So, PySpark features and advantages, right? And now, as compared with these different technologies, now try to say first one as compared with Stage. What is the advantage you are going to get with Spark, right? In-memory computation, right? Where you won't see this in-memory computation in Sage. What you are not going to see in Sage, in-memory computation. So Spark feature. We doesn't have this in Sage. And what is the advantage of Spark over HANA? What is that? What you got in Spark? What you doesn't have in HANA, right? Distributed, right? Distributed execution. Okay. Now, what as compared with the MapReduce, what is the advantage you are going to see in case of Spark? Very high speed, right? Very high speed. First thing is very high speed, like 100 times faster, I say. And what are the other features? Flexible parallel process. What is that? Flexible parallel process. In the case of Hadoop, we cannot control the parallel processing. The case of Hadoop, we cannot control the parallel processing. Means by default depends on the number of blocks. But here in Spark, we can control the parallel processing. While loading the data, we can just specify how many partitions you want. 10 partitions, 100 partitions, 20 partitions. Based on that, they'll be distributed across those many systems and are executed parallelly, right? So the more parallelism, we'll get more parallelism, right? Yes. Is my voice clear to all? Once again, can anyone please confirm, right?
Your voice is clear, Vijay.
So, and one more, this Spark has got special libraries available, right? So it is good for iterative algorithms, right? It is good for iterative algorithms. And as I said, right, it supports advanced analytics. Spark supports advanced analytics. And one more thing, yes.
Hadoop also we can define the number of blocks. So here also we can define at the starting of execution of this PySpark
You're talking about the partitions.
partitions, right?
So here in the case of Hadoop, one second. Observe this example in the case of Hadoop and Spark. Assume you got some data, 240 MB, f1.txt. So if you are dividing into some blocks, assume that 64 MB blocks. 64 MB blocks, totally 4 blocks you get. 4 blocks means data is divided into blocks in Hadoop, B1, B2, B3, B4. B1, B2, B3, B4, right? data is divided into blocks. These blocks, each block is stored across one system, S1, S2, S3, S4. Means you have got some 30 systems available. 30 systems available. You are using only 4 systems to execute, to work on this, right? To process this data. I want more parallelism. Can you increase further more? I want to control the parallel processing. I want to increase. I want 10 systems to run parallelly. Can I do?
Yes.
Hello?
No.
Yes.
How come?
Maybe we can do repartitions.
So here B1, B2, B3, B4. Okay, you have given the file size, everything you have given. 4 blocks stored in 4 systems only. See, just I'll give a labor example. I'll give a labor example, right? A building construction. You brought a 20 labors. You brought some 30 labors for building construction. But you are giving work to only 4 labors, S1, S2, S3, S4, only for 4 people. And remaining 26 people are idle. But what is that? If you are given the work to all the 30 people, the work completes much faster, right? The works complete much faster. So this kind of distribute means here 4 blocks stored in 4 systems, only 4 systems running parallel. But now if I want to increase, I cannot increase the parallelism more. I cannot control it in case of Hadoop. But in case of Spark, I can control, I'm saying. We can increase that or we can decrease it. Increase or decrease can be happen, right?
But sir, if we again increase the number of blocks, then we can achieve the parallel processing.
Yes, parallel processing means yes, if you want to, every time you need to restart your cluster. Every time you need to restart your cluster. Whenever if you want to change the size, right, you need to totally restart the entire cluster. For doing for the every time if you want to change the block size, right, entire cluster you need to restart. Until then, it won't be reflected.
Okay.
But here in the case of Spark, directly we can control it. Right? So supports advanced and one more thing, right? Here. MapReduce and Spark, right? One more thing, and even some people ask during this. There's one more product given by Apache, right? Flink, Spark. Both are introduced. Both are, see, in the year 2016-17, right? When people got updated with Spark, and immediately there was a talk, right? Okay, Spark is going away from the market. It is getting outdated, and Flink is dominating Spark. So everyone try to update with Flink rather than Spark. So in the year 2016-17, right, when Flink was dominating Spark, and says totally Spark will be away from the market, right? So yes, it was correct. Both are introduced. First Spark was introduced, next Flink was introduced. Both are introduced. Both are introduced by Apache only. Both purpose and objective. Both purpose and objective is same. Both purpose and objective is same, right? What purpose? So first Spark and next Flink. Flink dominated Spark. Means it dominated Spark means uh, Spark was weaker. Spark was weaker in data analytics, right? in data analytics in its initial versions, It was weaker in data analytics in its initial versions. Okay, it was weaker in the case of ML, machine learning, these kind of right. It was very weaker in this kind of in its initial versions. So if you see before Spark 1.6 version, before Spark 1.6 version, Spark before Spark 1.6 version, Spark Flink dominated Spark. From Spark 1.6 version, so from Spark 1.6 version, Spark came with powerful libraries. Spark came out with powerful libraries for this data analytics, graph algorithm, streaming, all this, right? Spark is almost equal to Flink. But from Spark 2 version onwards, right? Yes. Totally Spark again dominated Flink. So many libraries were introduced for this ML streaming and this graph algorithms, right? So in the initial versions, it was weaker, right? In the case of this ML algorithms, graph algorithms, right? But while introduced from Spark 1.6 and one Spark 2 version onwards, totally it again dominated Flink. Now, yes, again, Spark is running in the market. So in memory computation, distributed execution, very high speed, right, as compared with other processing technologies, right? Flexible parallel process, good for iterative algorithms, right? Most of these ML algorithms are iterative, supports advanced analytics. And one more like multi-language support. Multi-language support. It supports multiple like Python, Scala, Java, or language. And as I said, as compared with MapReduce, right? Here, in the case of one more major advantage, what you see, transformations can be reused. Transformations can be reused, right? Yes.
The transformation can be reused means mappers can be reused.
Not in not in the case of MapReduce. PySpark I'm talking, right? PySpark doesn't have that MR MapReduce. But here there is no concept of mapper reducer in Spark. So how these transformations can be reused, I'm going to say, right? In the case of art, we have got RTD's concept in that I'm going to discuss. Today, just I'll give an example, right? How transformations can be reused in Spark. So two things I'll be discussing with an example, how transformations can be reused. The one more thing is you need to clearly understand these features. Persistence, the main feature of PySpark, persistence you need to understand clearly. Lazy evolution, in-memory computation, right? These three things, main features, persistence, lazy evolution, in-memory computing. I'll discuss this with some examples. How this persistence and how these transformations can be reused. But before that, just I'll give introduction to the Spark data object, RTDs, RDD. Resilient, you need to clearly understand this. Resilient, distributed data sets. Resilient distributed data sets, right? See, Hadoop data objects. Hadoop data objects, files. Spark data objects, right? Spark data objects. So in Hadoop, data is stored in the form of files, Spark data objects, RTD. RTD is again subdivided. Observe clearly. RTD is again subdivided into partitions. It's again subdivided into partitions. A bigger Spark data objects, that is RTD, subdivided into partitions. These partitions are distributed. These partitions are distributed across multiple RAMs of multiple worker nodes. And are processed parallelly and are processed. Yes. RTD, see this RTD, right? Resilient RTD programming style. RTD's programming style is data flow. What is data flow? Is a sequence. It is a sequence collection of. It's a sequence collection of pipes. It's a sequence collection of pipes. Pipes means I can say RDDs. Sequence collection of pipes, RDDs. What is a pipe? A pipe, nothing but RDD. Is any data operation. Is any data operation. Such as. A pipe is any data operation such as loading data. Any data operation like loading data, transforming data, filtering data, grouping data, merging data, etc. One thing more we need to understand clearly, Spark data flow. Spark data flow. See, data flow, are they executed parallelly or sequentially? Data flow, are they executed sequentially or parallelly?
Sequentially.
Sequentially, right?
Yeah.
One pipe output will be the input to the next pipe. The next pipe output will be that input to the next pipe. All the pipes can't execute parallelly, right? Output of one will be the input to the next. The output of one will be that. So here, Spark data flow is executed. Spark data flow is executed sequentially. It is executed sequentially. That is sequential. That is RTD by RTD. Understand here, RTD by RTD. One after the another. One after the another. In that style. One after the another in that style. With in-memory computing feature. With in-memory computing, right? That means directed acyclic graph. With in-memory computing feature. and persistence feature. See here, two RTDs can never execute parallelly. Understand here? Two RTDs can never execute in Spark. We have got RTDs, right? Two RTDs. One RTD output will be the input to the next RTD, right? So two RTDs never execute parallelly. But if a RTD has 40 partitions, then those 40 partitions can execute parallelly, right? Yes. Okay. It's see in Spark, Spark data objects are called as RTD. So this is an RTD, Spark data object. It is divided into partitions. P1, P2, P3 in the same way, right? P20, right? Yes, P20, P1, P2, P3, P20. All these 20 partitions can execute parallelly. Twenty partitions or 40 partitions, all these can execute parallelly. But you got RTD1, RTD2, those two can't execute parallelly, one after the other. Yes. So just I said I'll be discussing about two things. How transformations can be reused in Spark, and what do you mean by persistence in Spark? Two important features in Spark: persistence and how transformations can be used. For that, check this. Observe this data flow. Observe this data flow, right? R1, R2, see, there are three flows here. This flow 1, this flow 2, this is flow 3. Flow 1, try to say, yes, everyone, I want the sessions to be interactive. Try to say, what are the RTDs which are part of flow 1? RTDs which are part of flow 1. R1, R2,
2, 3,
R-
4,
R4,
5,
R-
6.
R6, R7. Flow 2, try to say the RTDs part of
R4, R8, R9.
R1, R2, R3, R4, R8, and R9.
R9.
Flow 3. R1,
R2,
R-
R3,
is
R4.
the data flow, right? R1, R2, R3, R4, R
10.
R11, R21. Okay. So that's fine. Now, executing flow 1. executing flow 1. If you want to execute this entire flow, they are not executed normally. Lazy evaluated, right? Lazy evaluated. If you perform an action, right? R7 dot action on R7 means at the bottom RTD, it is going to execute from its root RTD to this R7. If you perform R7 dot action, from R1 to R7, it computes R1 output, takes R2 output by R3, R3 to R4, R4 to R5. Means during this process, during this flow process, data will be transformed, data will be filtered, data will be transformed, data will be merged. Many operations will be performing. Once data comes to R7, R7 is your final output. So if you perform R7 dot action from R1 to R7, if I say R5 dot action, on R5, if I perform whatever actions I'll discuss, but if I perform an action only, then the entire flow executes from its root. If I say R5 dot action, from where the flow executes, from where to where? From R1 to R5, R5 output will be collected. If I say R3 dot action means flow executes from R1 to R3 and R3 output is collected. So on which RTD you are performing action, right? You are saving R7 dot action. Then for R7, which is the R7 has to get the input from whom? R6. R6 has to get the input from R5. R5 has to get the input from R4, R4, R3, R3, R2, R2, R1, right? So it will start from the root. R7, whenever you say R7 dot action, now the data flow is going to execute from R1. First R1 gets loaded. Observe carefully here. R1 gets, don't think all the flow 1 RTDs will be loaded into RAMs. No. RAM cannot accommodate those many RTDs. One RTD is a bigger data object. All that RTDs at a time can't be loaded into the RAM. They can't be accommodated. That much capacity, RAM capacity cannot have, right? So first R1 gets loaded. R1 and R1 partitions. If you have got 10 partitions or 20, everything gets loaded and they will be computed. After computation, R1 output is taken as input by R2. Yes, check it. R1 to R2, R2 to R3, R3 to R4, R4 to R5, R5 to R6, R6 to R7. Now observe here. Yes. When R1 execution completed, the output is collected by R2. When R2 is loaded and computed, R1 gets removed from the RAM. When R2 output is collected by R3, when R3 is ready, means R3 is loaded and computed, R2 gets removed. When R4 is ready, R3 gets removed. When R5 is ready and loaded, R4 gets removed from the RAM. Now, when R6 is ready, R5 gets removed. When R7 is ready, this gets removed. When the total output is collected, R7 is removed. Now, what is in the RAM? Which RTD in the RAM? Which RTD in RAM? No RTD. No RTD is in the RAM. RAM is clear now. Again, you can trigger the next flow because no RTD in the RAM. Now our RAM is empty. You can trigger. You got the output. Total flow got executed. You got the output is collected. Now all the RTDs got cleared. Executing flow 2. Try to say executing flow 2. Yes. Same. What you need to say? To execute the entire flow 2. On which RTD I need to perform action? Everyone, try to respond. On which RTD I need to perform action? R9 dot action. Whenever we perform R9 dot action, From R1 to R9, it one by one it loads and computes, and R9 output will be collected finally. So first R1 to R2, R2 to R3, R4, R4 to R8, R8 to R9. So here what is that? When R1 gets loaded and computed, R2 gets loaded and computed. Once it is ready, R1 gets removed. R3 gets loaded and computed, R2 gets removed from the RAM. R4 gets loaded, immediately R3 gets removed from the RAM. R8 is ready and R4 gets removed. When R9 is ready, this gets removed. When the entire output is collected, R9 also removed. Now which RTD in the RAM? No, right? No RTDs are in the RAM. Similarly, executing flow 3. Flow 3, right? On which one I need to perform action? Yes. On which one? R
12.
R12 dot action. So here R1, R2, R3, R4, R10, R11, R12, right? Similarly, the same process here. When one is ready, the previous one gets removed. One this is ready and completed, the previous one gets removed. One is ready and this gets removed. When this is ready, this gets removed. Okay. Finally, when the output is collected, this also gets removed. Now, after executing the 3 flows, how many RTDs in the RAM? After executing the 3 flows, now how many RTDs are in the RAM within the RAM flow?
No,
Zero.
No RTDs are in the RAM, right? So you can trigger other flows, other flow executions can be done. But here, one drawback you are observing here. You are observing one thing, right?
Yeah, R1 to R4 is done many times.
R1 to R4, right? All the 4 steps are common in all that. Why again, you are re-executing that in flow 1, I executed, okay, from first to last. In flow 2, again, why you are re-executing from the beginning? Why can't you take this R4 output? R8 can take this R4 output and can compute R8, right? Why can't already R4 computation is completed, right? It's executed, it's computed, right? By in the flow 1. Flow 1 already executed, R4 got computed directly. Why can't it take R4 output and compute R8 and R9? This will be the flow, small flow, right? R8 and R9 will be the flow. If already R4 is available, if it is ready to give its output to R8. If R4 is ready, if it is available in the RAM. If R4 is available in the RAM only, it can give its output to R8, right? Hello? If R4 is available in the RAM only, it can give its output to R8 or R10.
Sir, on this, I have one question here, sir. So,
One second. I'll complete this flow, right? You can ask your queries. So my query is already R4 got executed, but it is not available in the RAM. If it is available in the RAM means, okay, the flow 2 can, this is the flow 2, R8 and R9. Simple, right? How many first 4 steps are decreased, right? Is flow 3 also, right? If R4, if it is available in the RAM, and if it is ready to give its output in the flow 3, all the first 4 steps are decreased in flow 3 also. This will be the flow, right? Now, if we observe here, in all the above 3 flows, even though the first 4 steps are common, always the flow is executing from the beginning. So to avoid this, identify the RTD whose output is mostly used by different flows. Identify the RTD whose output is commonly used by multiple flows and persist it.
here R4.
Persist is. How will you persist? You will say R4 dot persist. What do you mean by persist? Making the RTD available in the RAM. Even though the next RTD is ready also, don't remove this RTD. Even though the next RTD is ready also, don't remove this RTD from the RAM. Make this RTD always available in the RAM, so that if you execute any number of flows, it is ready to give its output to the different flows, so that to decrease the steps. Now R4 is persisted, right? Now check this. Now, 1 second. See how this flow is going to execute. When it's persisted, right? How the flow is going to execute, you check.
Since this R4 is persisted, and also we have distributed and parallel processing feature is out there, so we can execute 3 flows at parallel, right, sir?
Yes, I'll come back. Good query, right? I'll come back to it. Just keep your query and you can ask me after 2 minutes. R5, R6, R7, right? This is R8, R9. This is R10, R11, and R12. Without persistence and with persistence, observe the difference. R4 is persisted. Persisted. Now, executing the flow 1. No RTDs are executing the flow 1. What I should say?
R1 to R2.
R7 dot action. Without action, this flow won't execute. So first R1 to R2, first R1 gets loaded. And from R1 output collected by R2. R2 is ready and computed, R1 gets removed. R2 output taken by R3, loaded and computed, R2 gets removed. R3 output taken by R4, R4 is ready and loaded and computed, R3 gets removed. Now check this, right? Now check this. R4 output is taken by R5. Now here R3 to R4, now R4 is loaded, computed, and persisted. When R4 is going, understand here, when R4 is going to get persisted, when it is going to get persisted, when first time R4 is loaded into the RAM only, it will be persisted. After R1, after R2, R3, now R4 loaded into the RAM, R4 computed, it is persisted. Understand, when a particular RTD gets persisted, when it is first time loaded into RAM only, it will be persisted. Okay, now R5 loaded and computed. Do you think R4 gets removed? Does R4 gets removed? Hello?
Yes.
No, it's persisted now.
It is persisted, it won't get removed. Both available. When R6, R5 gets removed. When R7, R6 gets removed. Once R7 output is collected, R7 also removed.
Did they explicitly mention that this should persist or?
Now, which RTD is available in the RAM? Now, what is available in the RAM? What is in the RAM?
R4.
R4 available in the RAM, right? R4 available in RAM, right? Okay. Okay. Now, executing the flow 2 now. Flow 1 totally should execute. There is no other choice. But from flow 2, whenever you say R9 dot action, try to understand here. Whenever you say R9 dot action. So when R4 is persisted, do you think again will it execute from the start? First R9 dot action means it will check R9 input is R8. R8 input is R4. R4 available in RAM to give its output. Understand here? To execute R9, R9 has to get its input from R8. R8 input is R4, R4 available in the RAM. So the flow will be R4 giving its output to R8, R8 to R9. That's it. This is the flow. So it executes only R8 and R9. First 4 steps decreased, right? So whenever you perform any action, first it will check from the bottom, from where I need to start the flow from. If any RTD is already available in RAM, start from there. If not available, come from the starting. R9, R8 is ready, R4 won't gets removed. This is ready, this gets removed. Once the output is collected, this gets removed. Now, total output, total flow is executed, R4 in RAM still. If you are executing this flow 3, right?
First time when I did the flow 1, that time I did R4 persist command. When I did the flow 2, then also I have to give the persist command again.
Wait 1 second. Okay.
Yeah, when I did the flow 1, that time we have R4 persist command we have executed. So when we do
One
the-
second.
Okay.
First, you will define all the 12 RTDs. How many RTDs totally? 12 RTDs you will define. R1, R2, R3, R4. And you will say one more, right? R4 dot persist, that statement also you will provide. And which flow you want to execute? Flow 1 executes. Flow 1 executes means from the start to end it has to execute. There is no other choice. During this flow 1 execution, it has persisted R4. Then R4 is in the RAM now. Flow 2 no need to execute from the beginning. It is can execute from R4 onwards because R4 already available. R4 output already executed transformation. Its output you can take by R8 and compute on. But if you're directly executing flow 2 without executing flow 1, from where I need to start that execution?
Okay, from R1, then I
From
can
R-
again persist.
From
Okay.
R1 to R4 again. Because at least one flow has to get executed to persist that RTD. Also, the other flows can reuse that already persisted. Here in this flow 3, you observe R12 dot action, I will say R12 dot action. So once R12 action means it will check, okay, I need to start from where? How it checks? How it is going to check from where I need to start means it will check R12 has to get its input from R11. R11 input where it has to get R10. Is R10 available? No. Now R10 input is R4. Is R4 available? Yes. R4 in RAM. R4 available. So the flow is what? So the flow is R4 to R10, R10 to R11, R11 to R12, right? So once this execution completed, this gets removed. Once this is done, this gets removed. Once the output is collected. So in all the 3 flows, R4 is in the RAM. There's no need to execute from the starting from flow 2 and flow 3. They are not executing from the starting. They are not re-executing. As R4 available in the RAM, they are making use of that R4 output and computing the remaining flow, right? Instead of again re-executing them, right? So here, now after all the 3 flows, just like use and throw, you have just persisted R4, right? All the 3 flows execution completed now. Now should I keep R4 in the RAM still, or should I take it from the RAM? Now execution, all the flows execution completed.
Yeah, action is complete. We can remove it. Action is completed.
When all the flows execution is done, right?
Yeah. We can remove it R4.
Forcefully removing R4 from the RAM. How to remove that once your work is done, once that actions are completed, once the flow executions are completed, now if you feel that R4 is nowhere required, forcefully removing by saying R4 dot unpersist. R4 dot, whenever you say R4 dot unpersist, it happens immediately. R4 dot unpersist will happen immediately. Immediately R4 gets removed from the RAM. But one thing, whenever you say R4 dot persist, it won't happen immediately. It won't be persisted. Immediately R4 won't get loaded. Understand here? Whenever you say R4 dot unpersist, the operation happens immediately, it gets removed from the RAM. But whenever you persist, that it won't happen immediately, because to create R4, first until you execute this 3 RTDs, you won't get that R4, right? Understand here? Until you execute this first R1, R2, R3, you won't get R4. Understanding, right? Once you load R1, R2, R3, you compute, R3 output is nothing but R4. Whatever on the R3 you are performing some transformation, the transformation result is nothing but R4. That R4 you persist. Means when a RTD gets persisted, when first time it gets loaded, it will be persisted. Right? When first time it gets loaded, it will be persisted. Yes, when first time gets loaded, it will be persisted. Three ways to unpersist an RTD. 3 ways to unpersist. This is one way, forcefully unpersisting it, removing it. One is when session is closed, and when server shutdowns. So this R4 gets unpersisted. Yes, some query was asked.
So this R5 and R8 and R10, these 3 flows can be executed parallel, sir.
R5, R8,
R10 using R4 persistent.
they can execute. If R1, no, only 2 flows can execute parallelly. All the 3 can't execute. If flow 1 totally, if it has executed only, then the remaining 2 flows can take that R4 output. Understand, right?
But
Any one flow should first execute. For example, any one flow has to be executed, right? Then only the R4 gets persisted.
yeah, after R4 persisted,
Hmm.
then actually we have 3
R4 persisted means how it is persisted. Any one flow.
yeah, after execution of R4 RDD, so we have some output. So using that output, this R5 and R8 and R10, these 3 are three different flows.
Okay, you think that R4 dot action you did.
Yes.
Okay, R4 dot action you did, R4 got loaded and then
Yes.
persisted. Okay, next you want R5, R8 and R10.
Yeah, R10.
So all the 3 flows can take that available R4 output and they can compute parallelly.
Yes, that is my question, sir.
Yes.
Is that possible?
Yes. In this case, if already R4 is persisted, the 3 flow can execute parallelly. Yes.
Okay. But actually, how it would come to know after the execution of R5 to R7, R8 to R9, R10 to R12 to unpersist, because some flow may take long time. Some flow may take actually.
So already you are collecting, you are getting the output, right?
Yeah.
Already all the flows output you are collecting, right? Once you collected, now no, not required, right?
Oh, you mean like R7 dot action, R8?
Whatever the final output, the flow entire output you are collecting.
Mhm.
Yes. Once you collect it, now the flows execution is completed. Now not required, then you can unpersist it.
Yeah, so say for example, if at the time of R7 running, so I can't actually unpersist
Yeah,
it.
okay, you say what? After 3 flows executed, all the 3 flows output collected, or still you didn't get the output of a particular?
Yeah, still I did not get the output.
Then you cannot
Yeah.
do that, right? Okay. And one more, what is the major understood, right? Transformations can be reused, that is one. And what is persistence? That is 2 things you need to understand. And if we are taking a bigger flow, right? This is a small flow. If you have taken R1, R2, somewhere like R50 is there. R50 output is used by R70, by R80, and by R90. All these 3 flows are executing. So persist it. First time this flow executes, assume. From second time onwards, second flow, whichever executes, no need to execute from the starting. Directly from R1 to R80, R50 to R90, that's fine. Means 50 steps are decreased, right? Hello? 50 steps are decreased. Directly you are using that R50 output and computing the remaining flow. In flow 2 and flow 3, we are not re-executing from the beginning. So 50 steps are decreased. That is the advantage of persistence, right? Okay.
Sir, I have one query. Like all these RDDs are like workflow, right? The workflow that we see, like some transformation in one part and again second time one transformation. So these are like workflows.
No. See, RTD means, okay, first file is there.
Yeah.
From a file, RTD R1 gets created using Spark context text file. If you are loading and giving the path, this R1 gets created. On that R1 you got, right? On R1 dot some filter operation, you are giving some condition. The output R2 equal to, what is it? R1 dot filter based on some condition. R2 is created. The output of whatever you are getting. Whenever you perform any transformation on a RTD, the resultant is also an RTD. Whenever you perform any transformation on RTD, the result whatever you get is also an RTD. So whatever output you get R2 is an output. Again on R2, if you perform any grouping operation, any other transformations, right? The resultant whatever you get is nothing but R3. From R1, R2 got created. From R2, R3 got created. From R3, again, if you perform any transformation, right? You keep on creating until your desired output you get. You keep on transforming or you keep on filtering, right?
Yeah. So each of the blocks are supposed to do some transformation. So each RDD means some transformation or process that we need to apply on the previous data, like which is coming into it, right?
R1 will remains, R1 is immutable. It won't be modified or changed. R1 dot filter
Okay.
means don't think in R1 it will be
Yeah,
modified.
that I got. R1 is not
R1
changing. The
yeah,
output is,
the
yeah,
output,
it's like,
the whatever the output you get from the transformation is nothing but a new RTD R2.
okay. And
Again on that R2, you perform any operation, right? You get
okay.
R2 in this way.
Okay, so these all the RDDs are keeping itself unchanged. However, the data, whatever is flowing through each of these steps, that data is divided in many parts and getting executed parallelly. But
One
R1,
thing,
yeah.
I got one query. Everyone try to answer. Do you think R1 has got some 20 partition? Do you think R2 will also have 20 partitions in that? R1 is divided into 20 partitions stored across 20 RAMs of 20 systems. Do you think R2 also will have 20 partitions? Everyone.
It will have less partition as
No.
compared to
Doesn't mean that all the RTDs will have the same partitions. May equal or less than or equal to.
Yeah.
Okay. Yeah.
Yes, and on that partitions, you whatever logic, business logic you want to implement, you will get the output is an RTD. If you are performing any action, you will get a Python object. If you are performing any transformation, you will get Spark object RTD only. Understand? On an RTD, if you perform any transformations, I'll discuss one by one transformations and actions in the next session, right? Inbuilt actions and inbuilt transformations we got. If you perform any transformations means you will get Spark object. If you perform any action means you will get Python object. You need to understand that. So I'll be discussing about the actions transformations and the RTD computations, next to fault tolerance model and different ways of creating RTD. We have got a lot of discussions left out. I'll discuss in the next session, right? So fine. So resilient distributed access and what are that various actions and transformations you can apply on a RTD. Okay, fine. So that I'll continue in the next session, right? Yes. Next session, right? Same on next Saturday at 4 o'clock. But you are going to get a new link, right? Next Saturday, the link is going to change. If anyone who didn't get enrolled for this is try to get enrolled, and everyone who already got enrolled with the big data package, right? Yes, everyone, you will be getting the link to your mail IDs, or I'll be just posting in your WhatsApp groups who are already for Hadoop and PySpark, right? But people who are only for PySpark, who are getting enrolled for PySpark, try to get enrolled. Yes, for getting the link for the next session, right? So yes, next Saturday, the link changes. Yeah, fine. Yes, I'll forward the notes today, right? Yes. Today you will be getting the notes, what you have discussed, right? Yes. Okay, fine. So I'm stopping for now, and those students who are attending the scoop session, right, will be continued within 5 minutes time. Fine. With the same link of yesterday's. Okay. So I'm stopping here. We'll continue next week, right? Okay, fine.